Hello, I'm Graham Lewis, and in this video we're going to remind ourselves what present value is and obtain the general formula, the financial formula for the present value. So let's just remind ourselves. It's a sum of money which invested now at a given rate of compound interest will accumulate exactly to a specified amount at the end of future date. So let's think about that. Imagine I have an amount and I want to in the future it to be $100, and I don't know how much the present value is. I'll call it PV1, and imagine I'm just increasing it with one compounding 10%. So my multiplying factor is 1 plus 10%, 0.1, so a 1.1. So to find the present value after one compounding, PV1, it's clearly 100 divided by 1.1. So my PV1 is 100 divided by 1.1, which is $90.91. Okay? So that's just a reminder that if we invest $90.91 now, compound it at 10% once, we will have exactly $100 in the future. And so the cost of our annuity present value currently is $90.91. So expanding that into algebra using exactly the same idea, if I wanted my regular payment out to be R and I don't know what my current first present value is, PV1, and I know my interest rate is going to be 1 plus I, the interest rate per period, and it's really important that the periods match, that the period for I is the same as the period for N and the periodic regular payments for this to work. So therefore the present value after one accumulation is R divided by 1 plus I, which I have in the table there. Now that's the present value after one. Now if we go for 2 years, obviously the total, the sum of all present values will be, obviously I've got the one from the first year still, that's cost me that much money, R over 1 plus I, but how much will it cost me from 2 years? It'll cost me less money, and it will cost me less money because I'll actually be compounding more. I'll be compounding not once, but twice. So I need to divide there by 1 plus I squared. So this is the cost of the second year annuity, the present value of the second year annuity, PV2. This is PV1, and adding those together gives the total cost so far of all of my annuities, the present values. And then if I go after 3 years, I'd have the cost of the first year, R over 1 plus I, plus the cost of the second year, R over 1 plus I all squared, plus the cost of the third year, which obviously is compounded more, which was 1 plus I all cubed. Just a thinking question for you. Which of these numbers here, these annuities, are larger? Pause the video and have a think about that. You've got 3 there, three present values, the present value after 1 year, present value after 2, and present value after 3. Have a think, just pause the video, which one of those is the largest? Okay, hopefully you've had a think. Of course, this would be the largest one, the first one after 1 year, because you've only compounded once. So you need more money because you've got less compounding of that money. This is compounded twice, so this will cost you less. And this was compounded 3 times, so it'll cost you even less. So the terms will successively decrease. Hopefully you've spotted as well it's a geometric series, which as a mathematician is very appealing. So we can write it as the total cost here as the sum of the first n terms of all of our annuities. So this is the present value of the first annuity, this is the present value of the second annuity, and so on. This is the present value of my last annuity, which will cost me the least in terms of present value because it's got so long to compound and get bigger. And so this is a geometric series. So we have here that the first term is obviously R over 1 plus I, which we can see there. The common ratio to get from one term to the next term, we're multiplying by 1 over 1 plus I, and the number of terms is n. We have 2 formulas that we can use for the sum of the first n terms of a geometric series. Normally I prefer this one, and so I'm going to do that one, and we'll see which one works out might be nicer. So let's try this. So using that formula, you can see I put in my a, which is r over 1 plus I put in my little r, my common ratio, which is 1 over 1 plus I, and I get this badger here. Now I'm going to multiply the denominator by 1 plus I. I'm going to leave r outside. I'm going to multiply the denominator by 1 plus I, and I'm going to change this here, this 1 over 1 plus I to the power n. I'm going to change that to the inside the fraction there I can write as a 1 plus I to the minus 1. That's what that's to the power n. So hence I can write that as a 1 plus I to the minus n. So that's what I'm going to do on my next step. So you can see there on the top I've just left the r outside. I've changed the 1 over 1 plus I to the n to 1 plus I to the minus n. And on the bottom I've just multiplied the 1 plus I by 1 to get 1 plus I, and the 1 plus I by 1 over 1 plus I. The 1 plus i's cancel, leaving me with a minus 1. And what happens, nice and beautiful, the 1 and minus 1 cancels, leaving me with a lovely I on its own. That only happened because I chose my favourite formula, 1 minus r to the n over 1 minus r. Of course, a good mathematician chooses the best formula that's most efficient. This one would have been fine. I just would have ended up with a minus I on the bottom, and I would have had to multiply top and bottom by minus 1 to make my present value formula look good. So that's it. That's the present value formula, which lots of financial mathematicians use, and we've generated it using a geometric series. Try this proof yourself, think it through, make sure you understand it. There's nothing like doing it for yourself. I hope you've enjoyed the video and it's helped you understand present values, which can be quite tricky, and good luck with your mathematics and financial mathematics.